Yeah, actually, I was going to mention I didn't know that Jean-Christophe would be here, and I'm very glad to see him, but also a little afraid because he is one of the few people who is an absolute expert in iterated rational maps as well as interval exchange maps, and I'm going to talk about a vague dictionary between the two. So please reserve your criticisms for the end. Okay, so I'm going to use both the boards and the slides, so let me start out. So I want to, this is meant as sort of a preface. So I want to say a word about what happened in the study of dynamics of rational maps, or let's say even more precisely, iterated polynomials, and compare that to our current subject, which is Teichmüller dynamics. So the study of iterated polynomials starts with the study of unimodal maps, like x goes to x squared plus c, or they're often written in slightly different coordinates. So the study of this kind of dynamical system. Here, the critical point is periodic with period 7. There's lots of rich combinatorics, measure theory, and so on. It's one-dimensional dynamics. And this one-dimensional dynamics has an analog in the program this week, which is, of course, interval exchange transformations, which in many ways are akin to inverses of these multi-valued maps, with discontinuities coming from the branch points. So the next thing that one could say about the iterated polynomials is that one passes from the one-dimensional picture to the two-dimensional picture, or rather the dimension over the picture over the complex numbers. But before we do that, I want to draw your attention to a well-known figure in the theory of one-dimensional dynamics, which is the bifurcation diagram for the family of quadratic polynomials. And what this means is you consider a family of maps of the interval to itself of this type, and then you change the parameter, you change the value of c. And you iterate this map, and you find what the attractor of the map looks like in the interval. So it will be some set, which might be a finite set of periodic points, or it might be a more complicated fractal, or it might even be the whole interval. You find this attractor, and then you plot the attractor as a function of the parameter. And then the picture you get looks like this. So this is the parameter is moving horizontally, and vertically you see the attractor. So you have an attracting fixed point, and then it bifurcates to a cycle of order 2, and then 4. There's a famous cascade of period doublings. Here is the Feigenbaum point. And then amazingly, you can barely see it in this picture, there's some strange thing going on in this window up here, and if you blow up this picture, it's exactly a copy of the full picture that you see here. That's an instance of renormalization. So the next, one of the next steps one can take is to complexify the situation. After all, a polynomial acts on the full complex plane, and then you turn to the study of Julia sets. And in the same way, the one-dimensional interval exchange transformation can be lifted to the study of a holomorphic one form on a Riemann surface, or a flat surface, or a translation surface, and the corresponding horizontal foliation. And then you might say, well, I should say that also underlying this is the action of SL2R. So here I mentioned there's some sort of renormalization process which explains the reappearance of the same kinds of cascades over and over again. Here our renormalization operation is essentially the action of the group SL2R on the space of holomorphic one-forms. Okay, now Doherty and Hubbard really initiated the rebirth of the study of complex dynamics, dormant since the days of Julia and Fatou, by studying the complex quadratic polynomial. So there's sort of the simplest case are the quadratic polynomials because of the fact that they form a one-dimensional family over the complex numbers. There's one variable here, C. What's the simplest instance of Teichmüller dynamics? Well, one way to make that precise is to say what's the smallest dimensional invariant submanifold of the space of holomorphic one-forms. Now, of course, there are Teichmüller curves, but those are just single orbits. So there's really no dynamics. So the simplest case is when you have an action of SL2R on a locus here which is not come from a one-dimensional orbit, but something which projects to a two-dimensional locus in moduli space. And one of this such simple example, probably the simplest, is the eigenform locus in genus 2. So somehow genus 2 is a little bit like saying quadratic polynomials, but the eigenform locus reduces the dimension from the three-dimensional moduli space to the two-dimensional Hilbert modular surface. And I should also say that throughout this talk, I'm going to actually also allow one-forms on stable curves, especially those with compact Jacobian. So one-forms of total area 1. And the action of SL2R extends very nicely. So this is sort of our simplest example. Now, one of the great popularizing elements of this theory was the Mandelbrot set. So the Mandelbrot set is not an object that lives in the dynamical plane. It is some sort of description of the space of all quadratic polynomials. And its picture is so well known, I barely need to show it. I mean, here's one, but it's also on the copy of the Gazette des Mathématiciens that I just picked up outside. It's everywhere. And it is like a picture of all the Julia sets in the quadratic family at once. So it's a fractal object that somehow has many features that are similar to the features of the Julia sets, but it's not itself coming from a dynamical system. It represents a family of dynamical systems. So it's a sort of meta-dynamical system in the space of all dynamical systems. So you could ask, where is our Mandelbrot set that can be appearing on the cover of the Gazette des Mathématiciens next month? What is the Mandelbrot set in Teichmüller dynamics? And I don't have a perfect answer for this, but I want to present a possibility, which is, as in the case of iterated polynomials, we want to draw the simplest picture we can where we have non-trivial dynamics. So it will take place in the world of genus 2. Okay, so to describe the picture I'd like to draw, let me first give you a little experiment, which will be sort of like a version of this picture. Okay, so I want to consider the family of interval exchange transformations, but I prefer to use a circle rather than the whole interval, so I'm going to take a circle of radius 1, of circumference 1, and then my dynamical system will be rotating this by a distance of t. So that's my first transformation, RT. But now, since we're in interval exchange transformations, we're pretty happy to cut and paste in a piecewise linear fashion. I can then take this circle and mark off on it a subinterval of length L, and then let me just pull off this interval and glue its endpoints together. And so that will give me a small circle of length L the marking points will still be here. And then I can take the remainder of the circle and use it to build another circle of length 1 over L, a 1 minus L. And what I'd like to do on these circles is rotate by minus t. So what I want to, so the second map will be the following. You take this circle, you unglue it, and turn it into 2 circles. You rotate them by minus t, and then you glue them back up again so that they become the original unit circle. And so that's my second transformation, and I want to consider the composition of these 2 transformations as a map from the circle to itself. So this is a very mild variation of an ordinary rotation. In fact, it's almost a rotation by angle 0, because you move positively with distance t, and then you move negatively with distance t. So the map looks like it should be the identity, but the thing is you might sort of move from one circle to another if you move past the boundaries of this, the endpoints of the interval of length L. So in any case, at time 0, this map is the identity. And it's easy to see that for small values of time, it's periodic. So I'm going to let nt be the period of ft. Now, taking our cue from the case of quadratic maps, the period in this family of quadratic maps doubles each time you go through one of these basic bifurcations. So we might expect the period here to grow exponentially fast. So to get a good picture, I'm going to plot the quantity, the logarithm base 2 of nt. I'm going to plot this function as a function of t. The period may very well go up into the millions or billions for certain values of t. By the way, how do you compute the period? You don't iterate ft a billion times. You use Rosie induction, of course. Okay, so let me show you the picture that results from this very simple experiment. There. Okay, so what we see is we start out with period 1, and then the period jumps to 2, and it increases in some way. This is the log base 2, remember, so this is 2 to the 12. And then there's actually a point where the map does not have finite period. It becomes an aperiodic dynamical system, but then it sort of unwinds and becomes very close to periodic again. And then you see another spike, a sort of a place where the map becomes aperiodic. So I call these points where the period goes to infinity the bifurcation points in this diagram. Of course, you could call these jumps in the period bifurcation, but they're not really bifurcation in the sense that in this regime, we have periodic dynamics, whereas at these points, we have a qualitatively different, namely aperiodic dynamics. So the next thing you see is that there is a bifurcation, but then there's another bifurcation, and these occur more and more rapidly, and they accumulate at a point here. So we have a limit of bifurcations akin to the Feigenbaum point, like a cascade of period doublings. But then something even more complicated happens, namely, we have a second limit of bifurcations, and a third limit of bifurcations, and a fourth, and then we have a limit of limits of bifurcations, and so on. So so L was chosen at random to be pi over 7, one of my favorite numbers. But so L should be irrational. Otherwise, all bets are off. It's just a periodic map. But the qualitative picture you see is roughly the same for all irrational numbers. However, it's a good question. What maybe something even more special happens for certain special values of L. And indeed, well, so let me state 2 theorems. So the first theorem is that is that this bifurcation locus, B, which is the set of T such that Ft is not periodic. So this is just a subset of the real numbers, is a countable closed set that embeds homeomorphically in the ordinal omega to the omega. So this means it has limits, it has limits of limits, it has limits of limits of limits, and so on for every n, but then it doesn't have limits of those things. So it's similar in structure to the set of hyperbolic volumes, if you know what that looks like. And the second theorem is that if L is a quadratic number, that is, it's in some quadratic extension of Q, then B is self-similar about every point. And what I mean by self-similar is that if you pick a point in the bifurcation locus, there is locally a linear contraction of the interval that sends the bifurcation locus into itself. So that's a, let me show an example of that. Yeah, so here we have some cascades where the length lies in the field Q adjoining the square root of phi. They look better on my screen than on yours, but let me just try to explain what's going on in this picture. So here we see a cascade of here the point at time 0 in this family is actually aperiodic. And then in this family, near twice the golden mean, you see, down here, near twice the golden mean, you see a rescaled copy of this family. So this thing actually goes up and becomes arbitrarily high, and you see a copy of it here. And then you see another copy here, and these spikes are occurring along a geometric sequence, exactly a geometric sequence. And then here, we see a copy of this geometric sequence accumulating again at the golden mean. So that's a limit of bifurcation points. And then this whole diagram reappears inside here, again, exactly under a linear rescaling accumulating at the square of the golden mean. So the structure of the group of units in the space of, in the real quadratic field gives rise to some renormalization, which is visible in these bifurcation diagrams. Okay, so that was my motivating experiment. Okay, so let me now connect this. That was sort of the end of the preface. Now let me connect this to foliations of surfaces. So foliations of surfaces. So what's really going on in this example? What I'm doing now is going from 1 dimension to 2 dimension, the standard procedure to go from an interval exchange transformation to a foliation of a surface. So one way to picture this dynamical system as a continuous flow on a surface is the following. We start with a circle of circumference 1, and we build a cylinder. So now we have a little piece of a Riemann surface, and then we allow the top of the cylinder to acquire a pinch point. So it pinches down to a subcircle of length L and of length 1 over L. In between, we have a standard flat cylinder. And then these two pieces of the Riemann surface go off and have their own life for a while. And then they reconverge, sort of like particles in string theory. So we have a handle here and a handle here. And then they reconverge and they continue as a circle of radius 1. And then we glue this edge to this edge. So we glue the two ends together, and the result is a surface of genus 2. Now, on this surface of genus 2, if I've constructed it using flat cylinders, there's an obvious horizontal foliation. And just keep going sideways through each of the cylinders. So in other words, I get a Riemann surface plus a flat structure or a translation surface. In principle, it depends on the heights of the cylinders, but the dynamics of the foliation doesn't depend on the heights. So what's really important here is not so much a holomorphic one form as the harmonic form that's obtained as the imaginary part of a holomorphic one form. So this is rho is the imaginary part of omega. This is a harmonic real valued one form. And a harmonic form is closed, so it defines a measured foliation with isolated singularities. Now, how do I get the parameter t into the picture? What one can do is take a curve here and change the flat structure by cutting open and twisting by length t. So you perform a Dane twist of length t along a vertical closed curve here, and then along the corresponding closed curves here, you perform a Dane twist of length minus t. Okay, now these deformations give you honestly different surfaces with honestly different foliations. And another way to say what the diagram is that we drew is we looked at B, which is the set of T, such that the foliation of the harmonic form, rho sub T, is not periodic. Periodic means that all the leaves of the foliation are closed or that the surface decomposes into cylinders. So that's a lifting of the discussion to the theory of Riemann surfaces and harmonic forms or holomorphic forms. But something stays constant during this deformation. What stays constant are the absolute periods of this harmonic form rho. So associated to rho, we have a subgroup of the real numbers, which is just the set of periods of rho. So we integrate rho over the closed cycles in X. The periods will be, these absolute periods will be real numbers. And in fact, these real numbers form a subgroup of R isomorphic to z to the r. And in fact, in the case at hand, the subgroup is equal to just z plus z times L. And the reason I chose L to be irrational is so this subgroup actually has rank 2. So we refer to R as the rank of the form rho. And these absolute periods do not depend on t. So I should really put a rho t here. But since these cycles here are homologous to these cycles here, you actually get no deformations in the absolute periods. Where you get deformations are in the relative periods of rho. That is, if you integrate along a path that goes between the two zeros of the form, namely these two branching points of the surface, then this distance can change, or that integral can change, but the integrals along closed cycles remain the same. So this is a family of harmonic forms with fixed absolute periods. So what I want to do is quite generally associate some invariants to a harmonic form, or more generally to a closed form on any manifold. So here are some of the invariants one can make. Well, the first invariant is the following. So I take my form rho and I write it as the sum of AI CI from 1 to R, where the CI are integral cohomology classes. The statement that the rank is R says exactly that this is possible, and the coefficients AI are linearly independent over Q. And then by integrating these coefficients CI, I get a map from the Riemann surface X to what I call the period torus, which is just R to the R mod Z to the R, or if you want to be very fancy, it's the periods tensor R modulo the periods. And on this period torus, we have a natural one form, let me call it alpha, which is the sum of AI dxi from 1 to R. And the pullback of this one form by construction is rho. So just the data of this one harmonic differential gives us, by use of the integral structure, a map from our surface to a torus. And on this torus, there's an irrational foliation defined by alpha. By irrational, I mean each of the leaves is isomorphic to R to the R minus 1. It's codimension 1, and there's no topology to the leaves. And this map pi has the property that pi sends the leaves of the foliation of rho into the leaves of f sub alpha. So it's sort of this map linearizes the foliation on the surface, and sort of the geometry of the foliation is then hidden in this map pi. Okay, well and I should say that from the data rho, this map pi is well-defined up to homotopy. So it's a well-defined homotopy class. So one of the invariants that you can build from this homotopy class is the following. So you can think of rho as being an element of the one-dimensional cohomology of X, obviously. But you can also think of it geometrically as being like a diffuse one cycle on X. For example, if the leaves of rho are closed, then you get sort of a weighted family of closed loops on your Riemann surface. So that defines a geometric cycle, an element of H lower 1. And so there's a nice class which I call the flux of rho, which is just the image of the foliation thought of geometrically in the first homology of the period torus, now with real coefficients. Okay, so that's my first invariant. Now the thing about this first invariant is it's easy to see that it only depends on the absolute periods of rho. So it's a nice invariant for my family, but it doesn't change in my family. So it's not going to detect when these bifurcations occur, for example. So this is an absolute period invariant. And by the way, this absolute period invariant is simply a sort of intrinsic version of the well-known SAF invariant of the original integral exchange transformation. In particular, when the SAF invariant vanishes, this invariant vanishes as well. And the vanishing of this invariant is equivalent to the condition that these CI lie in a Lagrangian subspace of the cohomology of X. Okay, so this invariant doesn't change as the relative periods do. So I'd like something a little more subtle that will record changes in the dynamics as the relative periods vary, and this is provided by what I call the content C of rho, which is a subset of H upper 1 of X with coefficients in R. it's a convex set, compact, and it's simply the set of cohomology classes you get by taking the form rho and restricting it, that is multiplying it by the indicator function of A for all measurable saturated sets A. And by saturated, I just mean that these sets are unions of leaves. So it turns out that the form rho times the indicator function of A is actually closed as a current when A is a union of the leaves of the foliation. And so this set sort of records all of the ergodic components of rho, or all of the invariant measures which are subordinate to the original invariant measure for the foliation F. So what this typically looks like is the following. It contains the origin, and it contains rho. And when rho is ergodic, that's all it contains. But if rho happens to split into some invariant, if the foliation happens to split into some invariant pieces, for example, if it splits into some cylinders, then the cohomology classes of those cylinders will give vertices on the boundary of this set. And so you get some interesting looking convex set in the cohomology, and it definitely depends on the relative periods, not just the absolute periods. Okay, so now let me bring both of these invariants down to earth a little bit in the case we're going to be mostly interested in, which is rank 2, and in fact, genus 2. So maybe for concreteness, I'll start assuming that X is of genus 2 and that my foliation is of rank 2. Rank 2 is the largest the rank can be if I want the flux to vanish, because as I said, these forms CI have to lie in a Lagrangian subspace, which will be at most two-dimensional. So now let's assume that the genus of X is 2 and the rank of rho is 2. So then we have a map. Our period map goes from X to a two-dimensional torus. So there's an obvious invariant of this map, which is its degree. That's an invariant of the homotopy class. So we can define the degree of rho to just be the degree of this map pi. And this equals 0 if and only if the flux vanishes. And in general, if the foliation is periodic, this implies that the flux vanishes. And in genus 2, it's not quite true that the vanishing of the flux forces periodicity, but it's almost true. Namely, if the flux vanishes and the genus is 2, then we get the implication that at least F rho is not minimal. It doesn't have a dense leaf. It decomposes the surface, in fact, into a union of two flat tori joined along an interval. And on each of these tori, the foliation is irrational and ergodic. So either one of these tori individually can serve as my invariant set here, and consequently the content becomes a quadrilateral. Now let me mention that one of the reasons I'm happy to give this talk at this point in the conference is that many of the topics I'm going to discuss I hope will resurface in future talks. And in particular, there's a famous counterexample to this implication that vanishing flux implies sort of nearly periodic behavior. This fails very badly in genus greater than or equal to 3. So this is for G equals 2. But in genus 3, there's a famous example due to Yokos and Arnaud. And in their example, the flux is equal to 0, but the foliation comes from a pseudo-Anosov mapping. So it certainly is ergodic, it's uniquely ergodic, and not only that, but it's, so to speak, renormalizable. It's invariant under an element of the mapping class group as a projective class of measured foliations. So this behavior that vanishing flux implies periodicity fails to hold on the nose in higher genus. However, the whole point of this discussion was to consider varying the relative periods while keeping the absolute periods fixed. And it appears from some simple-minded experiments that this phenomena is very unstable. That is, although the Arnoux-Yoko's example is there, if you change the relative periods a little bit, it tends to become periodic. Yes, Edward?
What do you mean by flux vanishes? Does it mean that pi is limited to the zeros?
Flux is this class, right? So it means that this class vanishes in H1 of the surface.
So all absolute periods?
No. This is so it means that, so the absolute periods come from this cohomology class, which does not have to be 0. For the flux to vanish, it doesn't mean that these are 0. Then the rank would be 0. It means that these integral classes have trivial intersection pairing. The integral of Ci wedge Cj is equal to 0 for all I and j. Okay? I should say the flux has a very intuitive meaning. Namely, you have this torus, E, and you take a leaf of your foliation on X, and you look at the image of this leaf over on the torus, and then you lift it to the universal cover of the torus, which is R to the R. And if you get a path which might wander off to infinity in a certain direction. Now, if you take another leaf, it might wander off to infinity in a different direction. The average direction at which the leaves move towards infinity is the flux. So the flux vanishing says that the leaves tend not to move anywhere in the universal cover, or at least if they move one way, then they also move the opposite way. It's a sort of balancing act. Okay. So these are two invariants, and so we had the flux, which is an absolute period invariant. Then we have the content, which is more perceptive. And then here we have the degree, but we're going to be interested when the flux vanishes. So then the degree will just be 0. And it will also only depend on the absolute periods. So to go along with the degree, there's a second invariant which sees a little bit more of the action and depends on the relative periods, which is what I call the degree plus of rho. And this just means it's the maximum of the degree of pi restricted to A. Whereas before, A is a saturated set. And it turns out that you can make sense of this degree restricted to a saturated subset of the surface. A fortiori, this number might not be an integer, but in the case we're considering, genus 2, it turns out to be an integer. And what is it doing? Well, you see, you have a map from this surface to a two-dimensional torus. If the flux is 0, that map is degree 0, but you can restrict the map to each of these subtori. And since these tori are glued along a leaf of the foliation, that leaf maps to something that lies on the leaf of the irrational foliation here. So the image of one of these tori is a closed cycle on the image tori, and the degree of that map is degree plus of rho. And of course, if the degree is E on this side, then it has to be minus E on this side for the total degree to be 0. Okay, so this is measuring the tendency of a part of the surface to map to the period torus with positive degree. Okay, so now I can amplify my theorem, but still up here. So the bifurcation set is a countable closed set, embeds in omega to omega. So there's an underlying statement where we use these invariants to measure the complexity of each bifurcation. Okay, so the theorem here is, so we let d of t be equal to the degree plus of x sub t rho t in this particular family, or in any family of Riemann surfaces of genus 2, forms of rank 2, where the flux is 0, then the bifurcation set is just equal to the set of t where d of t is positive. Remember, this is a non-negative integer, so it vanishes when you have a periodic foliation, but it becomes positive when you split into a connexum of tori. And the limit as s goes to t, the lim sup as s goes to t of d of s is less than or equal to d of t minus 1. Sorry, I think I wrote that backwards. Let me just consult my notes. Sorry, so let's see. So what I want to say is that the complexity goes down in the limit. So so I want 1 plus this is less than or equal to. I guess that's equivalent. Okay, so let me just say in words what happens. You use this degree to measure the complexity. If you have some points of complexity 3, and you take a limit of them, then the limiting point has degree plus 2 or less. And then limits of these have degree 1 or less. Yes? Okay, so this is not what is written. So tell me how to write it correctly. Thank you. Minus 1? Plus 1. Okay, yes, thank you. Okay, just a little inequality sign. Okay, so anyway, this complexity goes down, so there's a sort of evaporation of degree under passing to limits. And this is a phenomena that was, for me, completely unexpected. It turns out it has a geometric explanation, which is too long to give here, but is not too complicated. But you see it forces the derived sets of B to get smaller and smaller. If you take the points that are limits of points of type 3, then the complexity goes down to 2, then it goes down to 1, and so on. So this is responsible for the fact that that this countable set embeds in this simple ordinal omega to the omega. Okay, so that's chapter 2. So let me, in the time that remains, go on to chapter 3. I guess I've erased my dictionary, but chapter 3 is, let's move into parameter space. Let's go towards the Mandelbrot set. So for this, I need some definitions. Doing this the German method. Oops, not quite. Okay, so I want to move now to the space of the moduli space of holomorphic 1 forms on Riemann surfaces of genus G, and I want to allow also stable curves with stable forms on them as well. So this is the basic setting for much of this conference. So this is chapter 2. So we have the bundle of non-zero holomorphic one-forms over moduli space of Riemann surfaces of genus G. Elements up here will be denoted by a pair x omega. And we have the action of SL2R on this bundle. And that's, there's a lot of action going on here. The closed orbits correspond to Teichmüller curves and so on. And what I'd like to do, since I've been considering families where the absolute periods are fixed, is consider more generally the locus inside of the space of holomorphic one-forms where the absolute periods are fixed. Now, how do you fix the absolute periods of a holomorphic one-form? So the holomorphic one-form defines a map, again, from h lower 1 of x by integration of cycles against omega into the complex numbers. And let's suppose that this map is injective. So then the image will be a subgroup of C, typically dense, so certainly when the genus is 2 or more, isomorphic to Z to the 2G. And this has a little bit of additional structure. There's a symplectic form here. You can take the product of cycles. And so over here, you also have an integral valued symplectic form. So I call a submodule of C, which equipped of isomorphic to Z to the 2G and equipped with a symplectic form, a polarized module. And then we can look at all of the pairs x omega such that the image of the period map is the given polarized module L, where we transport the symplectic form from here to here. And I will denote that locus inside of A of L, inside of omega of m as A of L. Okay, so it's the set of x omega, or let me call it just the set of omega, such that the periods of omega, the absolute periods, are isomorphic to L as a polarized module. Okay, so these form the leaves of a foliation, which I call the absolute period foliation. It's easily described locally in terms of period coordinates, just those where only the relative periods are varying and the absolute periods are fixed. This is one leaf of this foliation. Well, I shouldn't say it's one leaf because generally speaking, when you have a foliation, a leaf is defined as a connected component. So it's always connected. This is specified by saying what this, the data L should be. So this is a union of leaves of a natural foliation, and it might not be clear whether or not it's connected. So let me just state a theorem about this A sub L, what it really looks like. So the first thing to notice is that L provides a marking of the homology of X. See, L gives you an isomorphism that going backwards by the period map gives you an isomorphism from some fixed model Z2G back to H1 of X. And that means that the periods of X lift. In other words, we get a map from A of L into the Siegel upper half space, HG, by taking X2, its Jacobian, with the periods marked by this isomorphism. So A of L sits inside of the Siegel upper half space of genus G. And it sits inside there differently than it sits here. Here it might very well be dense. So the theorem is that A sub L is isomorphic intrinsically as an analytic space to a standard slice of the Schottky locus. That means there's a locus sitting inside of HG, which consists of the Jacobians of Riemann surfaces, so it's the image of MG bar. I call that the Schottky locus, and A sub L is simply the intersection of this locus with a standardly embedded copy of the Siegel upper half space of one lower dimension. So this tells you a couple of things. First, that the analysis of A of L as an abstract analytic space implicitly involves the Schottky problem. But the Schottky problem is trivial in genus 2 and 3. That is, S sub G bar equals H sub G in genus 2 and 3. And so in particular, for g equals 2, this locus A sub L is isomorphic to the upper half plane. And for genus 3, it's isomorphic to H2, which is a three-dimensional space. Okay, now there's the next main feature is really the main point of the whole game. The main point of the whole game is that there's some sort of structure on A sub L which is a sort of meta-dynamical structure. So when we discuss flat surfaces and IETs, we have foliations of Riemann surfaces. We have one forms on Riemann surfaces. In particular, we have Euclidean structures on Riemann surfaces. Well, the locus A sub L admits natural Euclidean coordinates. That is, here the periods of the absolute periods are fixed, but what's interesting is to form the relative period. So if you take two zeros of omega, then you can integrate omega between these two zeros. And that's only well-defined up to a choice of up to an absolute period, but the absolute periods are fixed. So locally, as you move around in this space, the relative periods vary, and they provide natural Euclidean coordinates on the space. Because if you change the choice of absolute periods, this number just changes by translation. So in fact, you almost get a translation surface. The only reason it's not quite a translation surface is that you might permute the order of the zeros here. On the other hand, the zeros might also collide, so it's not quite a Euclidean translation surface, it's a stratified Euclidean space. And so the second theorem is that A sub L is a complete stratified Euclidean space. So Euclidean manifold. So in other words, it's made out of cubes fit together in some complicated way. And by complete, I mean it's complete in the intrinsic path metric coming from the Euclidean metric on each stratum. So this was a problem that was posed to all of us, or many of us, by Smiley and Weiss many years ago at the Hausdorff Institute. So this is a nice question that they proposed we resolve. Now, in the case of genus 2, this flat structure is very simple. How do you give a Euclidean structure on a Riemann surface? You just give a holomorphic one form. Well, except, remember, there's this ordering here. So this is not quite a translation surface, it's a translation surface up to sign. So in fact, on A sub L, we have a natural meromorphic quadratic differential, which records the variation of the relative periods. And it records this Euclidean structure. It turns this piece of our parameter space into a sort of wobbly flat surface. Now it's meromorphic, so it has poles as well as zeros, and those are an important part of the picture. But let me just say very explicitly what Q sub L is. So in the case of genus 2, a form has generically two zeros, and so it has one relative period. Unfortunately, to compute that period, you have to choose an ordering between the two zeros. So the quadratic differential is just given by, you take the integral from one zero to the other of the form omega. That's a function which is well defined up to sign. And so that's the relative period. Then you take d of this function, and then since it's only well defined up to sign, you square it. And so this gives some function, q of L of z dz squared, and the function q of L of z is locally a meromorphic function. Okay, so here is my candidate for the Mandelbrot set. It is a flat surface in parameter space that is recording a lot of the geometry of the Teichmüller flow. Now, you might say, okay, you forgot completely about the Teichmüller flow, SL2R, in this description. Let me bring it back into the picture. And let me bring it back in the picture by taking L to be my favorite example. So I want A of L to contain my favorite flat surface, which is the golden table. So there was gold also in Vincent's talk. This is essentially the same gold. It's the golden ratio. So, sorry, my dimensions aren't implausible here. It looks sort of like this. Okay, so this is the following flat surface. It's a symmetric L where the height and width are given by the golden mean, 1 plus the square root of 5 over 2. And then you glue opposite sides to get a surface of genus 2. So the absolute periods here are just OD plus I times OD, where OD is the ring of integers, quadratic ring of integers of discriminant 5, which is just Z adjoin the golden mean. And the polarization can be read off from the symplectic form on this particular surface. So this contains this particular one form, x omega. That's the A sub L I'd like to look at. Now there's a general fact, which is that the map that associates to a polarized lattice this leaf is sort of functorial. That is, A of G times L is equal to G times A of L. So in particular, if G times L equals L as a polarized module, then this is for all G in SL2R, then if G stabilizes L as a polarized module, then it gives an automorphism of A sub L. And so a typical theorem is the following. Let me just state it in the particular case of D is equal to 5. The group SLOD acts on A of LD by quasi-conformal maps, which are in fact Teichmüller maps for this underlying quadratic differential Q sub L. In other words, if we take the part of the special linear group that's realized by affine automorphisms of the pair H and QL, it contains this dense subgroup of SL2R, namely the matrices with entries in the ring of quadratic integers Z adjoin the golden mean. So remember, Z adjoin the golden mean is a dense subgroup of the real numbers, and this subgroup is dense as well. What are we seeing then when we look at this slice? We are seeing a discretization of the action of SL2R. We're seeing Teichmüller dynamics. And we're seeing Teichmüller dynamics spread out before us like a patient etherized upon a table. You have a two-dimensional picture, and you can see the foliations, you can see the directions of stretching, and you can intuit the action of all of these things. So what we've done is we've taken a Poincare section of the continuous action of SL2R, and we've turned it into the discrete action of this arithmetic group. Okay, so I guess, now when did I start? Okay, so there's a lot more. Okay, so there's a lot more I'd like to say, but let me end by answering just two questions. So the first question is what does A sub L look like as a flat surface when L is equal to this, when we're dealing with the golden mean? What does it look like as a geometric object? And how is it made complete? Okay, and so to do this, I'd like to actually draw some pictures of A sub L. And I wanted to draw these pictures for about 4 years. And then Martin Möller and Zagier produced a beautiful formula which brought this dream within reach. They gave a formula for this form, Q sub L, and I then had the good fortune to visit the Max Planck Institute for a semester, and I spent months writing a computer program to draw this foliation. And some of you have seen it, but I can show you again the fruits of my labor. Okay, so let me just give you a preview. So I finally got this. Okay, shouldn't say Panasonic, but something's happening. There we go. Okay, so this is where we left off with these similar cascades. So let me now draw for you a picture in the upper half plane of the foliation produced by these by this quadratic differential. So sort of this candidate for the Mandelbrot set in Teichmüller dynamics. So I'm going to have to skip a couple of things here. So here is the beautiful formula of Möller and Zagier. It's a quotient of theta functions and their derivatives. There's a beautiful explanation for why it should look like this, but I'll have to skip over that. And here is a picture of the foliations of the upper half plane for d equals 5. So I'm drawing the horizontal foliation of the quadratic differential. So as you move along the leaves of this foliation, the real part of the relative period between the zeros is varying. That means the dynamics of the horizontal foliation is staying the same. And in these large strips here, the dynamics is periodic. Here, you can sort of see a zero. There should be a three-pronged singularity there. At that point, the two zeros collide, and there's a corresponding pole right underneath it. That is where the surface of genus 2 degenerates to two surfaces of genus 1 joined at a node, and the foliation remains periodic on those two complex tori. So let me show another picture of this with the spine of the foliation illuminated. Okay, so here are the zeros and poles of the quadratic differential. So basically the strata of omega of mg give rise to the special points of the quadratic differential. Here is our favorite one form, the golden table. And then what are these guys here, the other zeros? These are what I call fool's gold. So they are one forms that look like they should be the golden table. Their periods are the same as the golden table. The induced symplectic form is the same as the golden table, but they are not the golden table. So this is an illustration of the failure of the holonomy map to be a homeomorphism, to be injective. And as you can see, this picture gives a very nice way of enumerating these fool's gold tables. They fall into horizontal strips, and they're basically enumerated by two integers, and each one can be canonically paired off with a pole of the differential. And these poles can be described very simply because they correspond to well-known Shimura curves on the Hilbert modular surface. Okay, so this is basically what a picture of the foliation looks like. And so what you see is that if we were to try to go vertically in this foliation, there's a certain distance from this singular leaf to this singular leaf. And then there's a certain distance from this singular leaf to this singular leaf. And then there's another singular leaf underneath this, and so on. And it's not quite clear from the picture, but it happens to be true and is easily verified, that these distances form a geometric series. If this distance is 1, then this distance is 1 over the golden mean. This distance is 1 over the golden mean squared. So if you move straight down in this picture, you reach the edge of the picture in finite distance. And so obviously, the structure is not complete.
This is the distance measured using the flat metric and the quadratic differential?
That's right. I'm using the flat metric, and I'm just measuring the distance of the shortest path from this leaf down to this leaf. Okay? So there's a bunch of layers here. The layers get thinner and thinner, and yet supposedly, you look in some paper, there's an abstract proof that it's complete. How could this possibly be? Well, the way it can possibly be, and this is what took all the computer programming, is the picture down here doesn't quite look like the picture up here. It looks like this. And there's some leaves you haven't seen here. They're leaves growing up from the real axis, and terminating at other poles upstairs. And these other poles correspond to cases where the form degenerates to a net connect sum of tori with irrational foliations. And these irrational foliations have a degree, and the degree controls the structure of the accumulation points of these leaves. And these leaves are responsible for the completeness of the quadratic differential. So let me just mention one fact. Up above, we have the locus where the foliation is periodic. That's open and dense. What's left over is a countable union of leaves. The boundary of the periodic locus is not locally connected. In fact, it contains inaccessible points because there's some of these prongs that grow up, and there's an element of the SL2OD that fixes this point. And so then when you have another leaf coming by it, it gets wrapped around closer and closer and closer, and so there's no path from the outside avoiding these leaves, which can reach this one. So we see this really exotic, non-locally connected behavior, and I think a major interesting challenge is simply to give a topological model for the foliation that is being rendered here. Okay, but let me finish with my conceptual picture of what this surface really looks like. So I like to turn it upside down. Okay, so here is how I think of the surface as being built. So there's this initial leaf here, which I think of as a nice layer of fertile ground, and then there's some trees growing, some cedars growing periodically on top of it. They grow during the summer and the fall, and then the winter comes and they're buried underneath the snow. And there's a very thick pile of snow that lands on top of them. And then the next generation, more cedars grow on top of the snow, and these cedars are actually much taller than the previous cedars, and they're farther apart. And then the snow comes, and the snow is much thinner than last year, thinner by a factor of the golden mean. And then more cedars grow, which are much, much taller, and then another layer of snow falls, and so on. So you pile up all of these layers of snow. That's the part of the upper half plane where the foliations are periodic. Now, what about these countably many leaves? How do they prevent you from escaping through the snow? Well, if you try to burrow up vertically here and get out of this region, as you get very close to the real axis, you'll be forced into a region where the snow has piled like this. And if you're following a straight line for the quadratic differential, see, here's one of these weird leaves that grows up from the bottom. You'll be forced to pass through this leaf and then start burrowing back into thicker and thicker snow back to where you started. See, these contortions coming from these exotic leaves prevent you from escaping along a geodesic from the region below. So how can we sum this up in a picture that's comprehensible? Well, I want to show you the record of what happens when an explorer tries to escape. So what happens is he burrows through a layer of snow, and then a thinner layer of snow, and then a thinner layer of snow, but then he finally reaches this exotic leaf, and he's forced to go back to where the snow becomes thicker and thicker again. Well, then he tries again. But he's forced back again, and then there's a sort of double. He's foiled at a second level here and at a third level here. So in other words, the bifurcation diagram I showed at the beginning is a reflection in a simple experiment of these exotic leaves that we can now see in parameter space. And the mechanism which renders the space of absolute periods complete is the same as the mechanism that gives rise to this cascade of bifurcations. Okay, thank you.
Are there questions or comments? I was wondering about this theorem, which is still on the blackboard, whether it's lim sup, lim inf. I mean,
shall I state it correctly?
In this picture, the index here corresponds more or less to the value of d. D equals 1 corresponds to to isolated bifurcation, and d equals to.
Yes, that's right. Oh, I'm sorry. So I think the way I wrote it correctly at the
Exactly,
beginning
no,
was first. At the beginning was right. So, yeah, thank you. So,
But taking limb, you
so
go. You
let
go
me
up,
just
no?
make this right. So,
It's less
sorry.
or equal,
So so yes, it was correct as I wrote it initially. So what's happening is sorry, I said the words wrong. The complexity is going up each time you take a limit, and so you can only do that countably many times because it forces the complexity to infinity. Thank you for the correction.
Okay, other questions?
Yes?
Yes?
What kind of numbers do you get along, say, the first bifurcation? Instead of period doubling, you get, I don't know, Fibonacci or something?
What kind of numbers do you get? So the question was what kind of numbers you get here along these bifurcations. Well, I don't really like to look at the bifurcations of the periods because it's not quite, there's really several cylinders and they have different moduli. So for me, the most interesting bifurcations are these, where the period goes to infinity. And then they're self-similar by exactly quadratic units. The self-similarity comes from an element of SL2OD, in fact, an element of SL2Z that fixes one of the poles in the picture there. And it's just the leading eigenvalue of that 2 by 2 matrix.
The exact numbers, finite numbers, depend on L?
Oh, you mean what? Here. So for L, it's not self-similar. Oh, yes, right. So for L, something more complicated but completely predictable happens. You form the continued fraction expansion of L. You sort of do a Euclidean algorithm with L, and it gives you the sequence of numbers converging to 0 that appear.
Other questions? Yes?
So you said the leaf that you're studying are not complete?
Yes.
So can you give a geometric interpretation of what is a Cauchy sequence of surfaces which are not converging?
They are complete.
They are complete?
Yeah, that was the point. I think I wrote that. I hope somewhere down here it says complete. Yes, complete.
Oh, they are complete. Okay.
Yeah. So that was, see, the surprise was that it looked incomplete, naively. How is it made complete? How does it foil the explorer trying to escape?
And just to clarify, that's a statement for all genera, right? That's
That's a statement for any L.
Okay, that's it. Yeah, that's all I have.
Okay. No other questions? Okay,
Okay, thank you.